Okay, good evening, class. Today we are going to look at transaction management. I just need to make sure that I am sharing the right thing. Are you able to see my screen? Please confirm to me. I will not take for granted. I don't want to take it for granted, your patience thus far today. And I commend you and also commend the 2B day class for being able to come and attend with us. So the reason as to why I requested 2B to come in, because we missed our class yesterday. And I really don't want to keep you at different levels, especially for my section of the topics. So today we will be looking at transaction management. We will look at what it entails in terms of the characteristics of a transaction. We will also look at its properties. Thereafter, look at concurrency control, because we want to ensure that different people or different users are able to use the database at the same time, because that's ideally the purpose of the database approach. Having multiple users working at the same time and accessing the same data. But the goal is to ensure that we are able to do this without any interference. So we will need to study what concurrency control is and how the Dbms usually achieves this. Lastly, we will look at recovery control, that just in case failure occurs, how does the Dbms together with the DBA work hand in hand to ensure that we achieve a recovery. In other words, restore the database to the last consistent state. So when we look at a Dbms, we said it's one of those tools that support most of the activities of a database database administrator. And so he will be able to configure different aspects using the Dbms to ensure that we have a reliable set of data within the database. So we want to ensure that at all times, your database or your database system is in a consistent state. And consistent state, we are saying that we do not have inconsistencies in the data. It is reliable and valuable, just as we looked at other different indicators of quality data. So we want to ensure it's of quality, it is consistent, and we don't lose our data. So there are three main aspects that the Dbms focuses on, and I have already mentioned this. This is transaction support, the concurrency control, and the recovery services. So all this is to ensure that all the users work simultaneously with control measures put in place to ensure that we do not have chaos within the environment. So the first thing we will look at is understand what a transaction is. And in defining what a transaction is, it is important to note that it could be one action where you're just inserting data or deleting data or making an update to data already in the database, or it could be a series of actions. These actions are either performed by, okay, I don't know whether everyone is having a challenge with my network apart from Godfrey. I hope it stabilizes in a short moment. Okay, so we are saying that these series of actions that are performed are either done by a user or an application. You know, there are some of those activities that are already automated. You've written a program and it is automated. So that means the actions can be initiated by a program or by a user if you have human interaction for that given application. So it doesn't matter whether the user is a program or a human being. We are saying all the actions they perform should be able to transform your database from one consistent state into another. In other words, at all times, our goal is to ensure your database is in a consistent state. Being in a consistent state simply means that you are obeying all the constraints that have been defined. Those are the integrity constraints, as well as the business or enterprise constraints. In addition to that, we are simply saying all the quality indicators are satisfied, even as we had looked at data quality. The other important aspect of a transaction that we need to bear in mind is that we look at it as a single logical unit of work. In other words, if it is made up of a series of actions, we can only say a transaction has occurred if all the steps or actions have been performed. Okay, so if one particular, say if you wanted to withdraw money from an ATM and it comprises of 6 or 7 steps, all the 6 have to be performed for us to say it was a successful or a completed transaction. Otherwise, you would not look at it as having been successful. So a transaction is a logical unit of work that will move the database from one consistent state to another, obeying all the constraints, such that you can maintain the data integrity. And I am sure by now we all understand what we mean by data integrity. So just to add more light on the transaction, we are saying you can have just a single SQL command, or it could be an entire program that you've written, for example, the triggers and the stored procedures that you will be handling in your practicals. As a single command, I have mentioned you can have either an insert, a delete, and an update. And having passed DIM1, I am sure these are familiar territory for you. We know how to insert data, we know how to update, as well as to delete. So that can be looked at as a transaction. An application program is where you have more than one transaction with some non-database processing happening in between. But we'll look at examples to help us understand that particular point. So when we look at this example, we have 2 tables that we are putting into consideration, the staff table, as well as the property for rent table, on which we want to do the following transactions. So we have transaction A and transaction B. The goal of A is to be able to increase a staff member's salary. And this involves 3 steps. 1, reading what the current salary is for a given staff, in this case, X. And once we find out your salary as staff member X, we would like to increase it by 1.1 and thereafter update your salary with a new value that we have come up with. So that is one transaction. When we look at transaction B, on the other hand here, we are simply saying that we want to be able to reassign. We want to be able to reassign the properties that are looked, which are overseen by a staff member X. Bear in mind that this property for rent is a table that has attributes: property number, street, city, postcode type, rooms in that given property, how much it costs in terms of rent, who the owner is, represented by the owner number, who the staff member overseeing it is, represented by the staff number, and lastly, we have the branch number. That is the branch which oversees that given property. So we are saying that we would like to do away with a given staff member X. So we go through for all property for rent records. That means look at all the properties within this table, property for rent. And within that, we want to do the following. Look at the number and the staff number. So where the staff number is X, do the following. We want to reassign the staff number to another member of staff. So that means you have a new staff number. And once we have done that, we would like to update that record such that, for example, if you have a property number, a property 001, which is overseen by staff member X, we would like to change the staff number from X to Y and update that property number 001 is overseen by staff member Y, and then we end the transaction. So that is what this particular transaction is seeking: reassigning records overseen by staff member X. So these are just examples where you have a series of actions that make up a given transaction. So all these steps have to be performed for you to say that transaction B has completed and is successful. If one of them is not performed, that means you have not been able to achieve that logical unit of work. And therefore, there are two possible outcomes every time you are carrying out a transaction, and that is either a success or a failure. When we look at success, we are simply saying that this is where your transaction performs all the tasks therein or actions and commits. When we say commits, that a transaction has committed, we simply mean that the effects of that transaction. For example, if we looked at this transaction A, it means that we have been able to pick out your salary and increase it by 1.1, and we have updated it in the database. Okay. Once we make a change to the database in main memory, your hard disk, then we say that that transaction has actually committed. So committed transactions are those that have their effects or their updates reflecting in your database. And so we are saying that success is when a transaction commits and the database reaches a new consistent state. Every time we have committed transactions, we are saying we are not expected to lose that update. And therefore, if it was a mistake, for example, if you went to make a deposit and you deposited money on a wrong account, the only way we can sort out that mistake is by doing a reverse or a compensating transaction. A compensating transaction is one that will reverse the effects. So since you've deposited in a wrong account, it simply means the only way you can make sure you retrieve your money is by withdrawing the money from that given account and then deposit it in the right account. So here the compensating transaction is the withdraw. If you deposited 100,000, withdraw 100,000, that will return the balance of that given account back to what it was before the deposit was made. So take note, every committed transaction, the only way you can reverse the effects if it was a mistake is by doing another compensating transaction. The other outcome of executing transactions is failure. And failure is where we abort or we cancel a transaction. That simply means that if there were 6 steps to be performed and you were able to do only 4 of them, then your database is not consistent and you haven't, the whole logical unit of work hasn't been successfully performed. And so we roll back such a transaction. In other words, undo everything that you had previously done, such that you can return the database back to its original consistent state. And therefore, we are saying that we have 5 possible states in which a transaction can be. It can either be active, partially committed, failed, committed, or aborted. So when we begin a transaction, it moves into the active state. Active state, that simply means we are in progress of performing the actions that make up a given transaction. So until you've finished all the steps, that transaction remains in an active state. If we successfully do all the actions involved or all the steps involved in a transaction, then we use the upper arrow, that's end transaction, and move to a partially committed state. Before I move on, I would like to ask us to type 1 in the chat if active state is clear to you. If the active state of a transaction is clear to you, please type 1. Okay. There is somebody called Elisa, and I don't know how to pronounce this name. Starts with a Z. You have to.
Risky, madam. Could you please come again?
I come again. I'm not sure
Yes.
what exactly, but since I have very many words, once I will ask one of them to explain and we see if you will be able to get on board. Samuel Bulime, are you able to explain what you've understood? Let's verify that you've understood what I said. Yes, Samuel, kindly unmute. So what is your understanding?
Madam.
Good evening.
So when a transaction has started, its beginning, it can be. Hello? Hello? Oh,
Yes,
hello?
we can hear you, Samuel.
Are you able to hear me?
Yes, sir.
Hello?
Yes, sir. Okay, Samuel's network is a bit challenging. I'll request him to type it in.
State. It means when the transaction has just started, as the beginning of the transaction begins.
Kind of skipping Samuel. Ivan, would you like to come in? Unfortunately, I can't get you as well, Ivan. We can also use the chat to be able to type our answers. Yeah. Yes, Jesse. Jesse, you are unmuted. Would you like to explain what you understand by active? Okay, Sky. All right. A state in which the transaction has started and it's in progress. Great. Still in progress. Has started, but in progress. That is what we mean. Is it clear, Zeneli? Zelensky. Okay. Zelensky, is that clear now for you?
Yes, it's clear, madam. Thank you.
Great. I hope I finally gotten the pronunciation of your name. Okay, so once we complete, that means we are moving from the active state. We have done all the steps. We end the transaction and move to the partially committed state. In the partially committed state, I would like us to bear in mind that most of the processing happens in RAM, okay? And we store our data in the main memory, which is the hard disk. So the question here is, it needs to be transmitted from RAM to the hard disk in order for us to say that our effects have been made permanent. So through the commit action, we move from partially committed to committed state. In the committed state, the effects of the transaction are reflected in main memory where the database is. Is partially committed and committed states clear for each one of us? I will ask for a 2 if it is okay, for a 1 if it is not. If partially committed is okay for you, kindly type a 2. Okay, we have some ones of people who haven't understood. Okay. Job, what exactly is not clear about partially committed? About the RAM? So that wasn't.
Madam, I didn't get like exactly where. Like, is it like from RAM to what? Like that's why I didn't get from RAM to
Okay.
some. Like when it's transferred
Processing,
from the RAM, then where does it?
it goes to the hard disk. You know, you have a hard disk. I'm sure you did computer literacy and you know RAM and you know ROM. Yes? Our ROM is where you have your main memory or your hard disk permanent. Yeah? RAM is the random access memory where processing usually takes place. And therefore we are saying that we move usually once updates or computations have occurred in RAM, you have to send back those updates into memory, making them permanent. A good example is when you're typing a Word document. If you don't click save, what happens? David? What happens when you do not click save? David, you are unmuted. What happens?
You lose everything.
If you don't have to save innocent, by default, you're going to lose your data. Yeah? So that means you could have typed all your coursework, and at the last moment, just before you click save, power goes off. Your data gets, your whole coursework is lost. Yeah? And so we are saying at the partially committed state is like that Word document where you have written all your coursework, but just before you click save. Commit, that arrow between partially committed to committed, is equivalent to your save button. It transfers your data from RAM and makes it permanent in your hard disk or wherever you are storing your data. So we are saying partially committed is a state whereby you have finished all the transaction activities or actions. However, the updates haven't been made permanent yet. So if anything happens at that state, for example, if power goes off, we all agree, unless there's an autosave, you're going to lose your data. And that loss of data is equivalent to this arrow that is coming from the partially committed down to the failed. This abort is where we are losing our data. So I will ask Sadat, West, David, Twaya, not sure how they pronounce that name, and Job to tell me whether it is now clear.
Clear.
Okay, it's clear for Job. Sadat, are we at the same page?
Madam, to me it's now clear. I can understand it, like I know it now.
I beg your pardon?
Like I've got it.
Like you've got it. The best way to say that is I have got it, not like. Like means is a possibility that you haven't, but I will take it that you have. Great. So
Got it.
want to believe that active state is clear, partially committed is clear, and so is the committed state. So I will move to the failed state, and this is the state in which we can arrive at if an active transaction, in the middle of an active transaction, you encounter failure, something happens before you finish all the activities. simply a partially committed state, a transaction can commit or abort. Yes, Samuel, that's true. Okay. So if you are in the active state, that means you're performing still the actions therein of a transaction. If failure happens, if an interruption occurs and you can't finish all the steps therein, we move to a failed state. Remember, we said a transaction is a logical unit of work, a single logical unit of work. We perform all or we perform none. So if you've performed half of the actions and encounter a challenge, we count that as a failed transaction. And so we abort, we cancel it and move to the failed state. If during transmission of a completed transaction, we fail to commit it to the hard disk, we get interruptions, we also say that has moved to a failed state, and therefore it simply means we go to an aborted state. Aborted state, this is where you have to undo if there were any effects of an active transaction or some steps that had been performed already. In the aborted state, we undo them. You go and undo the transaction, the steps that you had done, so that you go back to the original consistent state of the database. Bearing in mind that every transaction we do is only successful if we move from one consistent state into another consistent state. So as long as we are not going to have a new consistent state, that means we have violation of some of the constraints, we need to abort. And that means get to an aborted state whereby you go back to the original database state that you had. If you are clear with all these states of a transition, of a transaction or transition states, kindly put 3. If you're home and dry, let's put a 3 and we move on to the next thing. Great. Okay. So once we have understood the different states in which our transaction can be, and we know the outcomes, you're either successful or we have failed, the next thing that I would like us to examine are the properties. Abdallah would like us to talk about the end transaction. Chemtai, please throw more light on that question that Abdallah has posted in the chat. Chemtai.
Good evening.
Good evening.
Yes, please. Good evening.
Yes. Chemtai, are you saying anything? Okay, Abdallah, when we say end transaction, if we begin a transaction, what do you think end transaction means? Because at the beginning here, we have a begin transaction. Begin, we are in the active state until we end. So what do you think end means?
I think it's when like you stop the action from taking place.
I beg your pardon?
It's when you stop the action from taking place.
Okay, we don't necessarily stop it, but it means we have done all the activities, all the actions involved in the transaction and reached the end of it.
Okay.
Makes sense?
Thank you, madam.
Okay. So I'd like us to look at the properties of transactions, and these are usually represented with the acronym ACID. So the ACID properties of transaction, the A stands for atomicity. And when we look at atomicity, it is known as the all or nothing property. This we have highlighted before. And we are simply saying that since we are looking at a transaction as being a single indivisible unit of work, all operations must be completed. Otherwise, don't do anything. That means we abort that given transaction. We stop carrying it out. Either do all operations or actions that define a given transaction, or do none. A simple example, again, is an ATM withdrawal. If I am doing a withdrawal at an ATM, I should have the money in my hands at the end of it. If I do not have the money at the end of it, I don't expect that deduction to reflect on my account. So either do it in completion until I have money and you reflect the new balance, or we abort that transaction and do anything that could have taken place if the failure occurred at the time of issuing the money, and do all the other steps that are before that given step, and ensure that my account balance still reads the 100,000 that was there before I tried to make a withdrawal of, say, 10,000. Does that make sense to us? Abdallah, atomicity. Acid in full, by the time we go through all the properties, you will get what it is, but the A we are looking at represents atomicity. It is the all or nothing property. Are we all home and dry? Sempa? Are you okay? Mchibi? Are we home and dry? Great. Okay. So to ensure this, the DBMS has the recovery component that ensures that we have atomicity. So just in case some components were done, we want to ensure that it remains so, and so the recovery component will redo, if there is failure, will redo what was done before to ensure that it reflects. Otherwise, it will undo all other actions that were done before the failure occurred. The other property, the C represents consistency. And when we talk about consistency, we have said when transactions are performed, we must move from one consistent state into another. We mentioned that consistency is about ensuring that all the rules and regulations or integrity constraints are satisfied. So anytime you perform an operation on your database, we must be able to move from a state where all the rules or constraints are satisfied to another new state in which the rules are still being satisfied. If you're inserting a new member into your database, or a new record is being put in a table, we are saying the primary key must have a unique value and it should not be null. If it's a composite primary key, we are saying that all the attributes that comprise of that primary key should have values which are together form a unique identifier. So those rules have to be satisfied at all times. And this is the responsibility of the integrity checker of the Dbms, but it also works hand in hand with the programmers. Remember, we say business rules and or enterprise constraints are usually programmed. You write a script to enforce them, the triggers and the stored procedures. So if the programmer made a mistake while defining a trigger or creating a trigger, then you can have issues about inconsistency. And that's why we are saying it is the responsibility of, yes, the integrity checker, which will counter check to say that all integrity rules are being satisfied, and the programmer, because the programmer has already set a set of rules in, say, a trigger that need to be counter-checked to ensure that the business rules are being satisfied. I will ask us to put a thumbs up if you are sure that consistency is clear. Okay, one person. Only one person is okay. Okay, we have 2 people. All right, 3. Okay, Alora needs more explanation. What about the rest of us? Those are only 4 people out of 72. You prefer to write a figure. Okay, let's write 5 if we are home and dry. 5 if it is clear. Type 5 in the chat if you are clear with what we mean by consistency. Okay, Enos, we have 3 people who are having challenges. Marvin, could you kindly unmute and articulate where you're having a challenge? Marvin, why is it not clear, or what is confusing you? for the sake of Marvin and Lillian and Aloro. Ochen, could you and Rashid, could you kindly tell us what you've understood by consistency? Ochen?
Okay, good evening, everyone.
Good evening.
Okay, when we talk about the consistency as a property of transaction, to me, what I understood is that, of course, when we are entering in data, one of the things we must put into mind is that we must actually maintain the values we enter. For instance, if a value is a primary key, it must be in every step that we enter in values, and that we must avoid actually duplications. Where there is duplication of any data, we shall not be consistent, and therefore the transaction will not be completed, which will actually force the system to roll back all what we have been doing. And that's why this property in transaction is very important to maintain. We must maintain the values we have been entering and also maintaining their constraints so as to receive a successful transaction. That's what I understand by consistency. Thank you.
Sorry. I have been talking to myself. Okay, let me go back. I am saying that, yes, consistency is about all rules and regulations being satisfied, as Godfrey mentioned. When we look at ACID, the I with the ACID acronym represents isolation, and this is about partial effects of an incomplete transaction should not be visible to other transactions. In other words, if one of the transactions is making an update to a value that you would like to read, it should not be permitted to read until updates have been made permanent. Because if you read it before it is made permanent or committed, chances are that the transaction that made the update will move from a partially committed state to a failed state. And that simply means that update will be lost. And if it is lost and you read in between, you will definitely have wrong answers for that subsequent transaction. So it is important to note that partial effects of an incomplete transaction should not be visible to any other transaction. First, wait for the update to be committed, then make it visible for another to take part, to make use of that data. And that simply means you have to have a strategy that when we have more than one transaction taking place, what kind of control can we put in place to avoid this kind of violation of isolation? And so it's the responsibility of a concurrency control component of a Dbms, and that is usually the scheduler. Okay, the component in charge of concurrency control in the Dbms is a scheduler. The last property of a transaction, represented by the D, is the durability. Durability is where we are saying every committed effect of a transaction or effects of a committed transaction are permanent and should never be lost, even in cases of failure. So if all of us have finished DIM 2 and say, who can I pick on? Mehdi has successfully earned himself 80%, which is a 5. He should not go to third year and look at his results and all of a sudden it turned into a 40 and has a retake to do. We are saying that 80 should remain 80 till he graduates and even comes back for his transcript and for any verification at any one time. So it is paramount that all effects of a committed transaction, we all understand what a committed transaction is. It's one which has completed all the operations or actions, and these have been effected or made permanent in your hard disk or your database. So the durability is the responsibility of the recovery component of the Dbms, that in case of failure, please find a way of restoring the data or the updates that were there before. So I would like to ask us if the ACID properties of transaction is clear. If this is clear, please type a 7. If the properties are clear, please type 7. Okay. A good representation, say they have understood, and therefore we will move forward. So to achieve all this transaction management, we have the database manager, which is in charge of most of the control, all the operations within the DBMS. And within the database manager, we are saying we have the transaction subsystem that is made up of 4 components: the transaction manager, the scheduler, the recover manager, as well as the buffer manager. The transaction manager is the coordinator of this particular transaction subsystem. And the goal is to be able to switch control between different applications. And it makes communication with the scheduler. I mentioned earlier that the role of the scheduler is to come up with a strategy or to effect or enforce a particular concurrency control strategy or protocol in order to ensure that different users are able to perform their different activities at the same time, however, without interference. That we don't have chaos. Everyone is doing their work and there is no conflict arising. The recovery manager, we have noted, ensures that you can restore the database into the state it was before when failure has occurred. So if failure occurs when a given transaction has begun, we want to ensure that you can go back to the original consistent state it was in. And that's the role of the recovery manager. Lastly, we have the buffer manager, whose responsibility is to efficiently transfer data from the hard disk to RAM. Okay. So the buffer manager really does a lot of work, especially from ensuring that we move from a partially committed to a committed state by transferring the data. And even when we are retrieving data, it's the buffer manager that picks it from the database to bring it into RAM. And those make up the subsystem that handles transactions within the DBMS. Are there any questions to that point before we start concurrency control? Okay. So as the word is, concurrency control, here we are looking at a process of managing simultaneous operations on a database without having them interfering with each other. In other words, we have 2 or more users or applications that would like to access a database. And in some cases, at least one of them is making an update to the data. Our goal is to ensure that this can happen at the same time. However, we don't want to have one transaction interfering with another, or the actions of one user interfering with those of another user. And therefore, we introduce the aspect of concurrency control. But before we delve into this, these activities can be done one after the other in sequence. When you do activities in sequence, you will never have interference. But now we want to have a scenario whereby they are all transactions are happening at the same time. In other words, we do some of transaction 1, sum of transaction 2, then we may do transaction 3, sum of them, then we do sum of 4, then we continue like that in an interleaved manner. So different intervals of doing operations from different transactions, but in a way that we don't have conflict and we don't reach an inconsistent state. So when we are trying to interleave these different transactions, there are chances of problems. And I would like us to first understand the kind of problems we could possibly have in order to know what we should guard against when it comes to concurrency control. An example of these problems that we are looking at, which are very common, is the lost update problem. Then we have the the uncommitted dependency problem. And lastly, the inconsistent analysis problem. Just give me a second. Three examples of the kind of problems that we can encounter when you're trying to have more than one transaction performing. We have the lost update problem, the uncommitted dependency problem, and the inconsistent analysis problem. So we will look at the lost update problem. Mommy. Okay, so when we look at the lost update problem, we are looking at a scenario whereby you have successful completion of the transactions. However, we have lost an update in the course of the execution of the different transactions. We will look at an example where we have two transactions, that's T1 and T2, where T1 is seeking to withdraw $10 from an account X, which initially has $100. And when we do at the end of transaction T1, what is the balance in X? What would be the balance of in account X? If it initially has 100, you'd like to withdraw 10, what value would you remain with?
$90.
Would remain with $90. Transaction 2 seeks to make a deposit of 100 into the same account. That means on top of the 90 that remained at the end of T1, if we add 100, that simply means our final balance is
190.
the end is Yes, Bob.
190.
190. Thank you, Samuel. 190. Okay. So let's follow this example and see one of the ways you can interleave, and depending on how you interleave, you'll either get the lost update problem or you will succeed. Okay, so we have 4 columns. In column 1, we are looking at time. We're looking at column 2, having the different operations that make up transaction T1, whose goal is to withdraw from account X. Transaction 2 is represented in column 3, where we seek to make a deposit of 100. And the last column 4 represents the running balance on account X. So at T1, the initial balance of X is 100, and we begin transaction 2. At T2, we begin transaction T1 and continue with transaction 2, whereby we read the value of X. When we read the value of X, that means we are looking at the initial value that is in account X, which is $100. At T3, transaction T1 continues by reading the value of X. At this point, no changes have been made, and so we will pick the same $100, which it initially has. At the same time, we continue processing transaction 2 by running the step where we make the deposit. So the new balance of X is equal to what we read, which was 100 plus 100. Okay. And so at that point, we still haven't made changes to the account balance. So at T4, transaction T1 continues with its action, where it calculates the new balance of X based on what it read minus 10. At the same time, T2 continues and here makes an update of 200 because the new balance is 200 and it would like to post this into the DB. So it makes a change from the initial 100 it read, added 100, the new balance of 200 makes that change. At T5, T1 doesn't know that there was an update that has been made. It continues its operation and seeks to update the database. So it sends its 90, whereas T2 closes shop, says I have committed. And so it commits its 200, makes it permanent. However, an update is taking place at the same time. And so we overwrite the 200 that should be there with a 90. T1 is satisfied having completed all its operation and makes it permanent. So rather than the 190 we expect, we have an update of only 90,000. What do you think happened here? Where is the challenge? We all agree that we have lost the updates made by transaction T2 because we only have that which was done by T1. So that means when we lose this update, it simply means that the wrong balance we are getting is we interleaved it in a wrong way. I'm sorry, West, we shall be able to send that link. Okay. So we are simply saying that we lose transaction T2's update, reason being T1 read while T2 was going to make an update. So we need to prevent the reading of this balance of X before the update has actually occurred. We need to ensure that an update has been performed before we actually read. So I hope the lost update is clear. Is it clear for us before we move to the next one? Type 1, if it is clear. Yes, Godfrey.
Actually, I thought that a transaction begins at T1.
I beg your pardon?
That I thought that the transaction begins at T1.
It can happen, they can all start at different points. T2 starts at T1, but T1 started at T2. Okay, Jesse is not clear. If it's clear for you, please type 1. Let me see the statistics. Are we all in Jesse's team? Or we have some ones in the class? Hamza, if your network is stable, could you kindly go through the example for us?
Good morning. Good evening, everyone.
Good
Yes.
evening.
The problem here is reading. When T2 is reading, for him, he reads 100. And when T1 also is reading, he reads the 100, you know? So when T1 read, he read the 100. So when he's withdrawing and he withdraws like the 10, he will assume the balance is what? Is 90. And when T2 is reading, he reads the 100. And when he makes this plus the 100 and writes like, it will be 200. So when you commit like this, you'll see that it is 90 here, then this one at the time of T6 is 90. Yes.
Thank you, Hamza.
Yes.
Thank you, Hamza.
Actually,
Whether he has made
okay,
it for
madam.
you, Godfrey. Yes.
Actually, I do think that T1 had it ready T2 before withdrawing.
Say that again.
That T1, actually, after T2 depositing the 100, we had to read it back in T1. So that we can have the 190.
So you agree with me, the challenge here is there is no coordination. Okay,
Yes.
what is okay. Let me just go over this again based on transactions don't have to begin at the same time. Remember, it's concurrency. When you go to your bank account, if you have a bank account, you are not bothered whether somebody is updating it, making a deposit or not. You want to get money or you want to make a deposit at that time you have gone to the bank. Am I right? Do you ask, are you bankers working on my account or not? Does anybody ever ask that?
No.
Another question I will ask, when you're doing a test online, do you ask yourself whether there are people already who have started or not? Your issue is, can I start my test and do it? Is that the case? Okay. So that simply means when a user comes to access the system, they would like to seek their service at that given time. Whether Swale was there before or David was there before, I care less. What I care about is that Mercy has come to access the database at this point, and I want to do my transaction. Okay, so you have multiple users coming in. So look at T1 and T2 as two different users who want to do different operations on the same account. One is making a deposit, one is making a withdrawal. So if there is no concurrency control, in other words, if the scheduler of the DBMS does not schedule these operations in a way that does not interfere with each other, the chances of interference are there. Okay, this is one of the examples of if you interleave it the way we have seen, that these are the different operations that are taking place at the same time, say T1 to T6, that is the time. We examine what is happening at T1, transaction T2 is beginning. At T2, transaction T1 also comes and wants to start. But at that particular time, T2 is making a read of the balance that is there. And we all agree at that point, no update has been made, and therefore it will read the initial balance of 100. At time T3, transaction T1 is continuing, it began. So it will read the balance. The question is there an update or there is no update? At that point, no update has been made to the balance, and so it will actually read the initial balance 100. Okay, at the same time, T2 is continuing its operations. Remember, we said here we are looking at simultaneous actions taking place, two transactions happening at the same time. So T2 is continuing just as T1 is also continuing. T2 makes an update. Unfortunately, T1, which started after T2, has already made a read, not knowing that there is an update to the balance. And so it will continue its operation based on a wrong value, which actually got updated at T4. Transaction T2 updates the balance from 100 to 200. Transaction T4 at that point, still at RAM, makes a deduction of 10 from what it read over 100, and at T5 makes an update, while T2 has completed. So T2 completes, it has made it 200, but at the same time, T5 came and made an update. They are all correct to do what they are doing. Unfortunately, in that way, in this interleaved manner, we ended up with a lost update. We lose the $100. So is it clear where we are coming from? Okay. It's clear for Jesse Nakato. Are we together? Yes, we are just trying to understand the problem. So it's okay for Jovan. I just want to know whether it's okay for you, Nakato. Okay. So I'll move on. And examine the second problem. The second possible problem is an uncommitted dependency. That is a dirty read. Is another word for this problem. And it occurs when one transaction is able to see the intermediate results of another transaction before it has committed. This is where we lose isolation. Remember, isolation of the property, we said we do not want to have those intermediate effects being read by another transaction. In case they are, this is one of the problems that you will encounter. So we have two transactions where one is actually doing an update, a kind of deposit, and unfortunately, it does not get to the commit state. It instead aborts and therefore reverses everything it has done. Unfortunately, T5 has already read its updated version and bases it on it to make its update. So let's just look at the example to make it come home and dry. So again, we have 4 columns where we have the time, then we have transaction. We have transaction 3 and 4. I think the other side I made a, okay. So in transaction 3, our goal is to be able to make a withdrawal of 10 on account X, while T4, the goal is to be able to make a deposit. So initially, X still has 100. So at T1, we begin T4. At T2, we read the balance. No updates have been done. T3, we make an update and we make sure that at T4, when transaction T3 is beginning, we make that update such that at T5, T3 is reading the updated value. Unfortunately, at T6, while T3 is continuing to make a withdrawal, T4 fails. It moves from the partially committed state to the failed state and therefore undoes everything that it had done and goes back to 100 rather than maintain its 200. So that means T3, which had already read, is basing on the 200 minus 10 to bring our new value to 190 instead of the 90 that it should be. Is this uncommitted dependency problem clear to us? It is clear that T3 was able to read the intermediate value or the update made by T4 before it commits or aborts. In this case, before it aborted. Put a 1 in the chat for yes, it is clear. If it is clear, kindly put a 1.
Madam, please come again.
Godfrey, I'm sure you have noticed when you tell me to come again, I don't know to come again on what. Eh? I don't know who said come again. Sorry, Godfrey. Yes, Jesse, your hand is up. Can I be of help?
That's talking about the transaction, the time T4, when T3 is starting, T4 is ending. Then at T5, we have that T3 is reading the balance, but T4 is rolled back. Now, when it rolls back from the balance of 200, going back to 100, T6 now reads the balance of 100 and it's deducting
the reading
10.
is happening. Jesse, the reading is happening at T5. Okay.
Yes, and it's
But
using the balance
the
of
rolling
100.
back hasn't occurred.
So the balance, the balance it's using at T6, is it the 200 or it's using the 100?
It's using the 200 because it read at T5. At T5, the balance is still 200. It's at T6 while it is making an update that we have a rollback. Is it clear, Jesse?
Yes, thank you.
Pardon?
Madam, it's clear, thank you.
Aaron, is it okay? Okay. So what I would like, to bring to our attention is be conversant of the time slots and what is happening at that given time, yeah? When you look at the time, see what is happening. And then you'll be able to know whether you will fall victim of the problem or you will have sufficed. If you look at the first challenge of the loss to update, the problem was that T1 was reading before the update was committed. Yes? Here, yes, T3 waited for the update to occur. However, unfortunately, there was a rollback and not a committing. It wasn't made permanent. So it read before knowing whether that update is permanent or not. So when it read, unfortunately, it was not permanent. So it's based on a wrong update. And so we are saying we should never read uncommitted data because one will have lost isolation and the chances of having this dirty read problem increases. The last problem that we are going to look at has several names, commonly known as the inconsistent analysis problem, but others refer to it as a non-repeatable or fuzzy read or a phantom problem, a phantom read problem. It occurs where one of the transactions is making several read operations of different values, while the other one is making updates. So if you do not coordinate properly when the read should occur, chances of reading an unupdated value are high, okay? So if one is reading values while the other one is making updates, there is need to have some concurrency control. But here is a scenario where that control wasn't performed properly. So you have T6, which is seeking to sum up the values in 3 accounts, that's X, Y, and Z. Whereas T5, on the other hand, is seeking to transfer $10 from account X to account Z. And so this is how the interleaving was done to lead to this challenge. So here we have 7 columns, the first being time, the second being transaction 5, T5, then transaction T6, and then we keep record of what is in each of the accounts, X, Y, and Z respectively, and finally, what is in the variable sum, that's holding the value of what T6 is seeking to do. Okay, so at T1, we begin transaction 6, and here all accounts have their initial balances of 100, 50, and 25 for account X, Y, and Z respectively. At T2, we begin transaction T5, and we initialize our variable sum to have 0. And so here no updates have been made. So the account balances for X, Y, and Z respectively are 100, 50, 25, and sum has an initial value of 0. At T3, we read the balance of X, and since no updates have been done, we have the value of 100. T6, transaction 6, also reads the balance of X, which is 100 at that point. No updates have been made to any account, and therefore the balances of Y and Z are still at 50 and 25 respectively, and the sum is still at 0. At T4, transaction T5 goes ahead to calculate the new balance of X by making a subtraction of 10, whereas T6 updates the sum variable by adding the initial value of 0 to what it read from balance from account X, which is 100. And therefore, we are saying at this particular point, we have 100 for X, no change has been made. We have balance 50, 25 for Y and Z, and our sum is reading 100. At T5, we want to make an update to account X based on the deduction made. At the same time, we want to read the balance of Y by transaction 6. And so the update is made. Our account X has 90 because we subtracted 10. Y is 50, and so that means the read by transaction T6 is 50, and the balance of Z remains at 25, and our summation is still at 100. At time 6, we read the balance of Z where no updates have been made, which is 25. We update our sum by adding what we found out in account Y to our balance of sum, which is currently 100. So 100 plus 50 gives us 150 as the new value for our sum. The value of X, Y, and Z stand at 90, 50, and 25. At T7, we make an update to the balance of Z. Remember, we read it as 25, and here we are adding 10, so we expect that, okay, so that's at T7. So at T7, we make that computation for the value, but no changes have been made, so we have 90, 50, and 25 for the respective accounts X, Y, and Z, plus the summation still holds at 150. At T8, we make the update or send the update to balance to account Z. So X still has 90, Y has 50, and now Z is updated to 35, and the summation of the sum still remains at 150. At T9, we complete T5 by making its updates permanent. That means X will be at 90 and Z will remain at 35 because it has finished. And we make a reading of the balance in account Z. Since it is 35, so transaction 6 holds that value of 35 for account Z. No changes have been made to the summation. At T10, we make an update to the summation by adding the 35, which is in account Z, to the value of sum, which is 150, giving us 185. And when we commit and make that permanent, we realize that rather than having 175, we have 185. Problem being, we read the value of X before it was actually updated. Because T6 kept on reading, but T5 was making updates, and we ended up reading an unupdated value of balance in X. So is this problem clear? If the problems are clear, I'd like different members to volunteer to tell me what things you observe that should be taken care of. So we'll begin by asking whether it is clear. So if it is clear, please type as C. If it is unclear, please type as 0. If it is clear, type C. If it's unclear, type as 0. Okay, we have quite a number of zeros. Fazil Baguma, could you kindly go through the example and we see maybe it is the English of the teacher that is stressing us? Please go over it again and we see if it can get clearer for our colleagues. Oh, Baguma, are you coming through? Jovan, do you want to explain us? Yes, Jesse.
Adam, I would like to answer Twakil in the chat how the sum goes from 150 from 100 from 50 to 150. When you look at transaction T4, at the time T4, transaction T6, they're saying that the sum equals to the sum of 0 plus the balance of X, which is 100. So we have that 100 first of all. So the sum has moved from 0 to 100. Now at transaction,
At time
T6, the transaction is the sum of 100 plus the balance of Y, the 50. That's how it goes to the 150.
Does it go to 100?
150.
Is it Twaha? Is that clear? Okay. Elisa, are you there already, or you still need a recap? Jesse, please go over the example to help the people with zeros to come to SC.
Okay. If I'm rushing, you tell me because I think I'll be faster about it. Starting
I
from
beg your
time
pardon?
T1, no, like I'm going to, I don't know that I'll explain it to the fullest.
We shall see, don't worry. Where you get stuck, we shall sort ourselves. We are all learning.
Okay. At time T1, we are beginning the transaction T6, but the balances in X, we have 100, balance of Y is 50, and the balance of Z is 25. At time T2, transaction T5 is starting, and in transaction T6, we declare the sum to be a 0. For the start, it's a 0. So the balances, we have not made any deductions on the balances in X, Y, and Z, or any increment. That's why the balances are the same for that. Then at time T3, we are reading the balance in X, and also we are reading the balance in transaction T6. So transaction T5 at time T3 is reading balance X, and also transaction T6 at time T3 is reading the balance of X. So all of them, they are reading the balances of X, transaction T5 and T6, and the balance of the balance of X is 100. But the sum, when you go over and you look at the sum, is still 0.
Yes, you're rushing.
Oh, apologies. Sorry. I'm saying at time T3, T5 is reading the balance of TX. Madam, if it's okay, help me more follow the cursor with the time so that they know what I'm talking about. At time T3, T5 is reading balance of X, and T6 is reading the balance of X also. So I'm saying that both transactions, T5 and T6, they're reading the balances of X, or the balance of X, which is 100. Now, when we come to transaction to time T4, balance X, which is 100, they are saying we are deducting a 10 for transaction T5. Yes, for balance for transaction T5, we are deducting a 10. But remember, the balance of X is 100. Now, in transaction T6, they are saying the sum, which was a 0 initially, we are adding the balance of X. Now, T5 is deducting a 10, but T6 is adding the balance of X. So we're having two transactions going on. One is reducing and one is increasing. So on the balance of X, we are deducting 10 in transaction T5, but in transaction T6, on the sum, which was initially 0, we are adding there the balance of X. Now, the balance of X at this stage is still 100. We haven't deducted the 10 yet. I don't know if I'm making sense. You haven't deducted. Okay, this is like a code. This is a command that remove 10. And you're saying remove 10, a comma, then you're saying also on the sum, add the balance of X before the 10 is removed. That is at time T4. So the sum is going to be increased from 0 plus the balance of X, which is 100. But at the same time, you're saying that T5, let the balance of X be deducted by a 10. Now we are having two transactions there. When we come to T6, that's where we shall get it. So we are writing the balance of X in transaction T5, and we are reading the balance of Y in T6. So the balance in transaction 5 at time T5 now reduces to 90. The balance of X has reduced to a 5. The balance of Y is still the same. The balance of Z is still the same, but the sum is now 100. We are there. It's not a 90, but it's 100. If the sum plus the balance of X was made at transaction T5, it would have been the 90 which had been deducted previously from the previous transaction of T4 at time T4. Now, at time T6, the balance of Z in transaction T5 is 25. The sum in transaction T6, we are saying we want the sum plus the balance of Y. Our sum now is 100. We are adding the balance of Y, which is 50. Now the balance 50 plus 100, that gives 150. That's going to be reflected in the column of the sum. When you look at the sum, it has been added the 100 previously plus the 50 of balance Y to give you the 150. But the transaction T5 was reading balance Z. I know that you're following that. That same time T6, T5 was reading the balance of Z. Now, at time T7, balance Z, we are saying we are adding there 10. And in transaction 6, we are doing nothing. So when we come to the balances, balance X is 90, Y is 50, and balance Z is 25. So we haven't added, we have we have written the command add the 10 on balance Z, but haven't pressed the enter key such that it is added. Now, when you press the enter key, that's at time T8, you write the balance of Z. And when you have to view balance, Z has moved from 25 to a 35. Then at time T9, we commit transaction T5. Then T6 reads the balance of Z. So we have ended the transaction T5. Now we are continuing with transaction T6. Only T5 has ended after us adding the balance of, after adding the 10 on balance of Z to give you the 35. Now, after ending transaction T5, we are going to transaction T6. At time T9 is reading the balance of Z. When it reads the balance of Z, it's a 35. The sum is still the same. Then we're having at transaction at time T10, we are saying that the sum previously, which was now 150, the sum, we are adding that the balance of Z, which is 35. Then at time T11, we commit transaction T6. Then when we commit, we have that the balance, which was 150, when we add the 35, it becomes 185. So when you commit everything, the balances have changed from 100. Balance X was 100, now it's 90. Balance Y was 50, that's the same. Balance Z was 25, now it's 35, and the sum moved from 0 to 185.
Thank you very much, Jesse. I see we have applauses in the chat. People have moved to see, and we have a hand clap. Thank you very much. And with that, I would, do you still have stamina? Or I can call it an evening for us.
Madam,
Pardon?
Adam, I think we should continue from there. We need to read these things. Some of us are not understanding very well.
I beg your pardon. Say that again. Okay. Lisa, what is the okay? You want to first process this. It is too much input. You have 4 hours, 4 consecutive hours. Okay, for purposes of keeping us at the same wavelength with everybody else, as is what I prefer, I will stop at this point and allow us to process, take it in, chew it, and ensure that by the time we come in next week, we are good to go. And I want to give us a warning that next week I will endeavor to be a little faster. So for us to be able to actually finish this topic before I take leave. So I wish you a good evening, and I know West, people are interesting. When I am telling them about giving me ones and twos, they don't want to